We're going to take a moment and do a mini solution review. So if we remember the definition of a solution is a homogeneous mixture of two or more pure substances. Homogeneous means there's no separation of phases, so things are evenly distributed. I shouldn't say thing, I should say the solute is evenly distributed in the solvent. Please note that there are different types of solutions. We can have a gas solution, most notably air would be a prime example. Liquid in liquid, which would be gas. A state of solution is liquid, the solvent is liquid, the solute is gas, that would be oxygen and water. All liquids, alcohol and water, solid dissolved in a liquid would be a liquid or aqueous solution, and that would be salt in water. Remember, we can have a solid solution made up of a solid solvent and a solid solute, and that would be something like silver and gold. In addition, we can have a liquid solute mixed into a solvent that is solid and have a solid solution, and that would be something like mercury in silver. Okay. Okay, what makes up a solution? Well, there are intermolecular forces between the solute and the solvent particles, and that attractive force is strong enough to compete with the forces between the solute particles and the forces between the solvent particles. Right? So when you have a pure solvent, you have certain intermolecular forces between those particles. And in a solid, you are also going to have strong attractive forces, be them ionic, be them intermolecular. And the idea is that the forces that are set up between the solvent and the solute are enough to overcome the forces between the pure solvent particles and the forces between the pure solute particles. So how does the solution form? And it forms by the solvent pulling the solute particles apart. So those solvent particles are going to surround or solvate the solute particles. And here's a picture of what the solvent particles would look like around one solute particle. Here is the solute sodium ion surrounded by the water molecules. Note the orientation of the water molecules with the partially negative portion of the water being attracted to the positive sodium ion. If we look at the chloride ion, this is obviously sodium chloride that is being dissolved in water. It is surrounded by the positive ends of the water molecule. Okay. So that ion dipole attraction, okay, is strong enough to overcome the lattice energy of the crystalline salt. So when we're looking at these energy changes in solution, we're looking at the solute molecules being separated. We're looking at the solvent molecules being separated, and then we're looking at these two separated solute and solvent forming the solution. Okay, and these are all energy changes. Remember from Hess's law, we can kind of break up a process into discrete steps, and the overall energy change is those discrete steps being added together. So it doesn't necessarily happen this way, but we can envision it happening this way, and we can put an energy change to it. If we look at an enthalpy diagram of this, we see we have the separated solvent, we have the pure solvent and solute. the change in enthalpy for the solution, okay, net exothermic process for this particular system. We have a change in enthalpy to separate the solute particles, another change in enthalpy to separate the solvent particles. Okay, and remember, we are working against an attractive force, so we're taking energy to separate those solute particles from each other. It takes energy to separate the solvent particles from each other. Now, when we set up the attractive force and set up those attractions between the solvent and the solute particles to make the solution, it is an endothermic process because we are essentially forming attractive forces. Okay, so there are also endothermic processes, and in that case, hopefully you remember from the energetics, why does that happen? Well, it happens because of the change in entropy. So types of solution, types of solution. Saturated solution, the solvent holds as much solute as is possible at a given temperature. And remember this, the reason why we're covering this again in the equilibrium section is because there is a dynamic equilibrium in a saturated solution. If you remember, saturated solution is going to have some of the solute in the solid form in equilibrium with the solution made of that solute and the solvent. But this is a dynamic equilibrium. Some of the particles are going from the solid into the solution phase. Some of the solute particles will be going back into the solid phase. Okay. There's an unsaturated solution, and that's when I don't have any of the solid present. I can add more of the solid, and that solid would go into solution because I have not saturated it yet. Okay, and then we have that supersaturated where there's more solute particles in the solvent than there should be. They just don't have a pattern of how to line up. So you put a little crystal in that, and you've given it the pattern that it needs to then set up the solid portion of that solution, and then you would have a saturated solution after adding the seeded crystal. Okay, there's a common saying that like dissolves like. That means that polar substances tend to dissolve in polar solvents. Nonpolar substances tend to dissolve in nonpolar solvents. And the reason is because of those energy changes. Okay. The more similar the intermolecular attractions, the more likely one substance is to be soluble in another. It is that amount of energy to pull those particles apart is about equivalent as the energy released to set up the attractive forces between the solvent and the solute. Glucose, which has hydrogen bonding, very soluble in water. Cyclohexane, which only has dispersion forces, is not soluble in water. Vitamin A, soluble in nonpolar compounds like fats, but vitamin C, with its very more hydrogen bonding, very soluble in water. If you look, this whole section of the vitamin A has no hydrogen bonding, so it's mostly nonpolar. It does have this one little section, but it's like this part of the compound outweighs any bit of hydrogen bonding in that one little part of the molecule. In general, the solubility of gases in water increases with increasing mass. Larger molecules have stronger dispersion forces, so they're going to have more dipole moments. Okay, if you remember those dispersion forces. The solubility of liquids and solids do not change appreciably with pressure. solubility of gas in a liquid is directly proportional to its pressure. Just open a bottle of soda, okay, and you release all of the CO2 from the soda. While it was under pressure, your soda doesn't go flat because you're holding that pressure in the bottle, and that gas CO2 remains in the soda. There is a law called Henry's law. Solubility of the gas is equal to K, which is a Henry's law constant for that gas in that solvent, and Pg is the partial pressure of the gas above the liquid. Okay, the partial pressure of the gas above the liquid. Wanted to show you a solubility curve. Okay, and what this is the solubility grams of salt in 100 grams of water versus temperature. And you can see that each one of these curves is identified with a different substance. As you can see, most ionic substances, their solubility increases with increasing temperature. There is at least one exception on this graph that decreases with increasing temperature. Okay, but generally speaking, the solubility of solid solutes increases with temperature in a liquid solvent. However, gases, their solubility again on the y-axis, temperature on the x, solubility of gases generally decreases with increasing temperature. Okay. Let's continue talking about ways of expressing concentration of solutions. We have a mass percentage, which is the mass of your solute A in solution over the total mass of the solution, and that's the mass percent of A multiplied by 100. Then you have parts per million and parts per billion. In parts per million, it is the mass of A in the solution over the total mass of the solution times 10 to the 6th. That's where you get the million parts per million. For parts per billion, we're going to multiply by 10 to the 9th, and that's where the billion comes in. There's something called a mole fraction. And hopefully you can guess that a mole fraction, and this is the moles of A over the total moles in the solution. In some applications, you will use the mole fraction of the solvent, not the solute. So pay attention to what it is you're doing, whether you need the mole fraction of the solvent or you need the mole fraction of the solute. Very important in some applications. Molarity we know, moles per liter or moles per decimeter cubed. Interesting thing to note about molarity. Since volume is somewhat temperature dependent, there are small changes in the volume of a liquid depending on the temperature. Molarity can change with temperature. That's why some use something called molality, which is a little m, which is the moles of solute over the kilograms of solvent. Molality will not change with temperature, since we're talking about number of particles and we're talking about the mass of the solvent. If we want to go from molarity to molality, we're going to need the density of the solution, and then you can go back and forth. Basically, pay attention to the units.